Hello and welcome to lecture 52, Turboprop engines. We are running with the course on aero engine gas turbine cycles. So in last lecture we were discussing about single spool configuration. We have looked at the construction of single spool configuration, and we have discussed like the turbine what we have defined it as a gas generator. At last we have given with say the numerical or tutorial. So today we will be solving that numerical. So let's discuss what all information we have for single spool or say turboprop engine, what all is discussed with. So here in this case, if we look at carefully, the informations are like the core mass flow rate is given, compressor pressure ratio is given, turbine entry temperature is given, we have exhaust jet velocity, that is 250 meter per second, we have information about different efficiencies and the properties. And here if we look at on the right hand side, we are having our TS diagram which is representing the whole process. So let's try to understand how do we proceed with the solution for this. So like the way in which we are always discussing, let's see what all are the information known to us. So very first component for our engine, it is intake, and for this intake it is given it's a flight, not a flight condition, it is my ground condition. So M infinity is 0. My diffuser efficiency is given, pressure and temperature they are known to us. So we can calculate what will be our exit temperature and exit pressure from the intake. The next component what we have is compressor, and for this compressor we have our compressor efficiency to be known, our pressure ratio is known, so we can calculate what will be our exit pressure and exit temperature from the compressor. The component what we have is combustion chamber, and for this combustion chamber the burner efficiency is given, total pressure loss is given, turbine entry temperature is given, calorific value of the fuel it is given. So based on that we can calculate what will be the exit pressure and fuel air ratio for the combustion chamber. Now since this is single spool configuration in which we are not having any information in terms of work distribution for say mainly what is the power required by the compressor, what is the power requirement by this propeller, and that's the reason why here we will be taking the approach what all we have discussed in last lecture with say ideal enthalpy concept. So we will be calculating what will be say our delta Hi. Based on this delta Hi, we will try to calculate what will be my work split between say the nozzle as well as between the turbine, and based on that we will be calculating what will be my nozzle exhaust velocity. Here in this case the nozzle exhaust velocity is given to us, so that's what will make our life easy in terms of calculation of say work split. Once we have that work split, we can calculate what will be the requirement of power by the turbine. We can calculate what will be the exit pressure and exit temperature from the turbine. With all this information, we can calculate what will be the performance parameter for this particular cycle. So let's proceed with. So make always habit to draw the line diagram for the engine and TS diagram. So let's look at very first component. The component it is our intake, and for intake our entry pressure and temperature they are known, and this testing condition is a ground condition, that means my M infinity is 0. We can calculate what will be say the exit pressure from the intake. We are given with the efficiency. Here in this case my pressure it is known, the efficiency value that is not given, so we can safely assume say 100% at this moment. Similarly we can calculate what will be say exit temperature. So this exit temperature that is coming as 288 Kelvin. So remember one thing, maybe you can assume the efficiency of the diffuser or intake, make a note saying like you have assumed this number. But if it is not given, then just go with straightway 100% efficiency. Okay. Now let's look at the next component. What we have is our compressor, and for compressor the pressure ratio is given, that is 10, and compressor efficiency is 87%. Based on this pressure ratio, we can calculate the exit pressure from the compressor, and that is 10 bar. The exit temperature we know that can be calculated based on the pressure ratio and the efficiency of the compressor, and this temperature that is coming 596 Kelvin. So now we have exit pressure and temperature from the compressor. The next component what we have is combustion chamber, and for this combustion chamber it says we are having drop of pressure by 2%. We have calorific value, turbine entry temperature. So let's try to calculate what will be the exit pressure from our say combustion chamber, and that is 9.8 bar. Now in order to calculate say what will be our fuel air ratio, that is very important. So for that we will be putting our control volume, and from this control volume we will write our energy balance, and based on that energy balance we can write down the fuel air ratio. It is given by H04 minus H03 divided by calorific value into burner efficiency minus H04. This value we are writing in terms of CpT0. Be careful here, hot and cold gas, that's what we are having. Say what is coming out from the compressor, we are considering the CpC, and for hot gas we are considering CpH. Let's put all this number. It says my fuel air ratio is coming 0.0192. Okay. Now up to here you are comfortable with in terms of doing the calculation, and I am sure you must have tried the calculation till here. Now let's move towards the next component. Here, as we have discussed, since this is gas generator kind of configuration where we are not aware of what will be the work extraction from the turbine, so we are not having the information about say 0.5, and that's the reason we have taken the approach in which we will be considering the isentropic enthalpy drop. That's what we are writing as a delta H, and that split we have done, it is in terms of alpha into delta H for the turbine and 1 minus alpha into delta H, that's what is for the nozzle. So let's move forward with this configuration. So this delta H we can calculate, it is nothing but H04 minus H09S. We have information about what is our exit pressure. Let's say we will be taking that as a atmospheric pressure. We have information about what is the pressure at the entry of the turbine. It says it is 9.8 bar. So if we will put these numbers, we can calculate what is our delta HI, and this delta HI it is coming to be 597.72 kilojoule per kg. Now the question is what will be our alpha? Okay, there is no information as such. It is given what will be the split, work split. Okay, but if you look at carefully what all information that what is given, it will give you some hint. Let's see what hint is given. It says here in this case, in order to calculate this turbine work, we need to have the value of alpha. Similarly, we have information about the exit velocity. There also we have this equation in the form of alpha. But here if you read the information carefully, the exit velocity from the nozzle, the number it is given, it is 260 meter per second. All other information, that's what is known to us. Delta HI we have calculated, nozzle efficiency is known to us, exit velocity is known to us. So if we are putting this in terms of our formulation, then it says my alpha is coming to be 0.94. So once we have information about this alpha, we can easily do the calculation for what will be the work split. So let's now take the turbine and nozzle configuration here. So turbine work output that we can write down in terms of, say, turbine efficiency into alpha into delta HI. It says this number is coming to be 505.67 kilojoule per kg. Say this turbine work that we can write down in terms of Cp delta T0. So here in this case T04 is known to us, so we can calculate what will be T05 or what will be the exit temperature from the turbine, and this number it is coming 761.05 Kelvin. Now what is our next requirement? That is what will be our exit pressure from the turbine. We know we have information about the turbine efficiency and the way in which we have solved earlier cycles. Same logic can be used here. So what we have is in terms of the relation for, say, expansion ratio that we are correlating in terms of turbine efficiency and the temperature. So all the temperatures and efficiencies, they are known to us. So let's put these numbers. It says my P05 it is coming to be 1.197 bar. So that will be the exit pressure from the turbine. Now let's try to calculate the next parameter, very important parameter. That's what is in terms of, say, my thrust, equivalent thrust power, thrust specific fuel consumption, or say equivalent specific fuel consumption. Let's try to calculate all these parameters. So very first thing that is required is in terms of calculation of power. This shaft power we know that we can write down in terms of mechanical efficiency into turbine work minus work, that's what will be consumed by, say, compressor, or work that will be extracted by the compressor. So if we are writing this equation, turbine work we have calculated, the compressor work we can write down in terms of Cp delta T0. If we are doing this calculation, my shaft work it is coming 186.32 kilojoule per kg. Okay. Now let's try to calculate the power. We know this power that is given by m dot into shaft work, and this is coming to be, say, 2794.87 kilowatt. So it's almost 2.79 megawatt. Okay. Now total power, that's what we can write down in terms of the power by my propeller plus this is what is representing by my core, or we can say that's what is by the jet. So let's try to put this correlation here. We will be calculating what will be the thrust that will be generated by the core or that will be generated by the nozzle. It is given by m dot into 1 plus f into V infinity. We have all these numbers. It says like my thrust that will be generated by the nozzle, it is 3974.88 Newton. So let's try to put these numbers in terms of calculation for the, say, total power. So if we are doing the calculation for the total power in kilowatt, then that is coming as, say, 2564 kilowatt. So this is what is the total power, that's what is required, or say that will be generated by this particular engine. We are interested in calculating the equivalent shaft horsepower, and this shaft horsepower we are calculating, and this is coming to be 3437 HP. Here this we are converting in terms of kilowatt to the HP. Okay, so do not get confused. We have the conversion by, say, dividing 0.746. Now once we have calculated equivalent shaft horsepower, we need to calculate what will be equivalent specific fuel consumption, that is given by m dot f divided by equivalent shaft horsepower. These numbers are known to us. Say f we have calculated 0.0192, and this m dot core also it is known to us. So we can do this calculation, that is coming to be 0.665 pounds per say ESHP in hour. Be careful here, this core mass flow rate, that's what we have converted from kg per second to pounds per hour. So this is a conversion factor. Okay. Now we want to calculate what is the thermal efficiency. You must have realized we have the thrust that is generated by the nozzle also. So my thermal efficiency formulation, it will be in terms of equivalent shaft power. So let's put that number, and it says the thermal efficiency is coming to be 20.70%. Okay. Now what next we want to calculate, it is in terms of overall efficiency. So here for the calculation of overall efficiency, as we have discussed earlier also, there are different approaches by different authors as well as engine manufacturing companies also. Some of them, they are writing the overall efficiency in terms of propeller efficiency into thermal efficiency. Here in this case, the propeller efficiency is not known to us. What is known to us is say gearbox efficiency into propeller efficiency, that's what is 0.75. But if you recall, we have discussed for conventional purpose for industries, people, they are safely assuming this propeller efficiency to be 80%. So let's take this propeller efficiency to be 80%, and if we are putting this propeller efficiency to be 80% and thermal efficiency to be 20.70, that's what will be giving the overall efficiency to be 16.56%. Now as we have discussed, there is other way also. It says the overall efficiency that can be calculated by propulsive efficiency into thermal efficiency. If we put the equation for the propulsive efficiency, that's what will be T total, or the total thrust that is generated by the engine, into V infinity divided by say total thrust into V infinity, and this is representing the change of kinetic energy. This is by our physical definition, what all we have discussed in our week 1. Now here in this case, what we know, it is a ground condition where my V infinity is 0. So it says my propulsive efficiency that will come 0. So do not get confused here in this kind of solutions. Okay. So just try to calculate what all is the exact meaning in terms of propeller efficiency and propulsive efficiency. Okay. Now in overall, if we look at, we have our V infinity to be 0, our temperature, that's what is 288 Kelvin at the entry, my pressure was say 1 bar, equivalent shaft horsepower we have calculated, that is coming 3437 HP. Equivalent specific fuel consumption we have calculated, it is 0.665 pounds per ESHP hour. We have taken our propeller efficiency to be say 80%. Thermal efficiency we have calculated, that is coming 20.70, and overall efficiency is 16.56%. So this is what is a solution for what numerical we have discussed with. I am sure this will give the confidence to you all in terms of doing the cycle analysis. Here in this case, we will not be discussing what all are the effect of variation of different parameters on the performance. That we will be discussing for the next discussion for 2-spool configuration, where we will be having detailed discussion of what all will be the effect of different parameters on the performance. So today here we are stopping with. In next lecture we will be discussing say 2-spool configuration, where we will be having free turbine kind of configuration, and we will be doing the analysis for that cycle. So thank you very much.